Welcome to lecture 16A on vector spaces. We have, in some sense, finished the very basic theory of linear algebra in that we've built a self-contained theory of vectors and matrices. There's a lot more that can be said about vectors and matrices, but one semester is not enough to cover it all. What we want to do next is we want to realize that what we have been learning isn't just a bunch of tools that are applicable to vectors and matrices, but also applicable to many other applications, where vectors and matrices are just the simplest examples, kind of like a toy example that helps us understand the bigger picture. I want to start with two simple but crucial observations that allow us to extend almost everything we said over the last 3 months to many other objects in mathematics. The first is this flowchart, which illustrates that almost everything we said in this class can be defined just in terms of addition and scalar multiplication of vectors. Although we have many definitions and algorithms, and some can get pretty complicated, everything boils down to simple definitions and concepts that are just addition and scalar multiplication. For example, take eigenbases, probably the most complicated concept from this class so far. It is a special type of basis. A basis is just an efficient way of describing a subspace where every element of the subspace can be written as a linear combination of the elements in the basis S in exactly one way. Both the concept of bases and subspaces can be described in terms of addition and scalar multiplication of vectors. An eigenbasis consists of eigenvectors. These are vectors in which matrix multiplication acts in a nice way, but matrix multiplication is just an application of a linear transformation. A linear transformation can be defined in terms of addition and scalar multiplication again. So everything boils down to addition and scalar multiplication of vectors. This is the fundamental idea of this class. The second important observation is that vectors are not the only things we know how to add and how to multiply by a number. Addition and scalar multiplication make sense for many other mathematical objects. For example, we know how to add two polynomials together. Here, I can add these two polynomials and get a new polynomial. I can also take a polynomial like this one and multiply it by a number 4. What I did here are addition and scalar multiplication, but instead of applying them to column vectors, I am applying them to polynomials. I can also add and scalar multiply other real valued functions of x that are not polynomials. Here I can take sine of x and add that with e to the x, and I get another real function of x. I can take the natural log of x and multiply it with a number and get another real function. Our goal in this lecture and the next few lectures is to take the whole class and generalize it as much as possible. We will replace the idea of vectors with other kinds of objects we know how to add and how to multiply by a number. We will start with a new definition. We need a name for a set of objects that behave like vectors. The standard name for this is vector space. A vector space is a set of mathematical objects such that we know how to add two objects to get another object in that set, and we know how to multiply an object by a real number to get another object in that set. We also need some axioms. It's not enough to say that addition exists. You also have to say that addition behaves like we would expect addition to behave. There's a bunch of properties that addition has that if addition didn't do that, we wouldn't be able to do any of the nice things that we like with addition. For example, we expect scalar multiplication to distribute over addition. Otherwise, we would not really want to call that addition and scalar multiplication. So a vector space is going to be a collection of objects with rules for addition and scalar multiplication that behave in the right way. There are 8 rules that tell us what the right way is. I'm putting them on the next slide because they may look a little scary if this is the first time you see them. I will talk about the axioms in a minute, but you should really think of a vector space as a set of objects that behave nicely, just like vectors. Unfortunately, this term is confusing because we will see that a vector space can consist of things that are not at all vectors, but just behave like vectors. A more appropriate name may be vector-like space. Elements of a vector space may not be vectors, as in columns of numbers in brackets. We will see that they can be things like polynomials or real valued functions or matrices that are not vectors. To make this worse, some references, like our textbook, use the word vector to refer to any element of a vector space, even when working with an object that is not a vector, as in a column of numbers in brackets. So just beware that some textbooks will do this. To avoid confusion, I will reserve the word vector to only mean columns of numbers in brackets. Here's the list of properties of axioms of additions and scalar multiplication. I will go through this, but I don't expect you to digest this. This is a list of the essential properties that make addition what we want and make scalar multiplication what we want. In that sense, these details are very important, but we will focus on the big ideas and not worry about remembering each axiom. Here are the axioms. First, if I add 2 elements of a vector space, I can add them in either order. This is called commutativity. Addition is also associative. It doesn't matter which sum I resolve first. I can resolve this sum first or this sum first. The third property is very important. It says that every vector space has a special element called the zero element, with the property that adding it to things does not change them. In the same way that we're used to having the zero vector for any size vector, we have the zero element in any vector space. There's also negatives. For every object in a vector space, I have a negative of that object such that addition gets back to the zero object. The essential properties of scalar multiplication include distributivity in both senses. Scalar multiplication is associative, and multiplying by the element called 1 does not change anything. These are all things that are nice, and if we didn't have them, we would miss them. And this should be your main takeaway from this slide. Probably the most important thing to remember is the existence of the zero element in the vector space. This is what you will use often. Let us look at some examples of vector spaces. The motivating example, the example that sets off the whole theory, is the example we have been working with this whole semester. The set of all vectors of a fixed height, Rn. If I have 2 vectors of the same height, I can add them and get a new vector of the same height. If I have 1 vector, I can multiply it by a number and get another vector of the same size. So the set of vectors of a fixed height is a vector space. The rest of this course will be mostly taking definitions and theorems we already know, crossing off Rn, and replacing it with the word vector space. We will take things we already know and redefine them for more general vector spaces. Our first example of a vector space that is not made of column vectors is the set of polynomials in X. We will denote this set by this boldface P. Given 2 polynomials in X, I can add them. Given a polynomial in X, I can multiply it by a number. So this is a vector space. When working with this vector space, something that can be potentially confusing is that there are many ways to write the same polynomial. So it can be useful to know when two polynomials are really the same. So here is a fact that you may already know. Two polynomials are equal if and only if they have the same coefficients when you write them in the standard form like this. You don't always have to simplify the polynomial in this way, but a big advantage of the standard form is it makes it easy to compare your polynomial to another polynomial also in standard form. I will now do the following 3 exercises. None of the arithmetic will be hard. I just want to focus on the ideas of linear algebra in this new context. We want to use addition, scalar multiplication, and linear combinations. These are the basic ideas in linear algebra. In the first exercise, I want to find a polynomial p so that 1 plus x plus p is equal to this polynomial. So I set these two equal and I will subtract both sides with 1 plus x. I can then simplify and I find this polynomial p. This was a very simple computation, but this is the type of question that makes sense in any vector space. In this exercise, we want to determine whether this polynomial is a scalar multiple of the second polynomial. We have to be a little careful because this polynomial right now is not written in standard form, so it is a little hard to compare. First, let's rewrite the question. Is there a scalar c in R such that this polynomial is equal to c times the second polynomial? Remember that scalar means number. First, let's put the left-hand side in standard form. I FOIL 2 factors at a time. Now I have this in standard form. I see that this left-hand side has an x cubed, and there is no way to get an x cubed on the right-hand side by scalar multiplication. So this is impossible. So this polynomial is not a scalar multiple of the second polynomial. Equivalently, this polynomial is not a linear combination of this polynomial. So this polynomial, the first one, is not in the span of the set containing just this second polynomial. We're taking these words that we're used to using for column vectors, and now we can apply them in any vector space, in any situation where vector addition and scalar multiplication make sense. Finally, let's practice working with linear combination in the context of polynomials. Here, I have one polynomial, and I want to see if I can write it as a linear combination of these 3 polynomials. We want to find 3 numbers, a, b, c, such that x squared is equal to a times the first polynomial plus b times the second polynomial plus c times the third polynomial. Here we should be a little bit careful. This is a polynomial in one variable x. The letters a, b, c are just numbers we're trying to find. Right now, this right-hand side is not in standard form, so we should put it into standard form so that it is easy to compare with x squared. So we want to replace these with something of this form. So we should collect all terms with x squared. The only term with x squared would be c times x squared. So I have c here. And I collect all terms with x. So this should be b plus 2c. And then I collect all of the constant terms. We should think of this one as x to the 0. The constant terms are a plus b plus c. The only way that the left-hand side and right-hand side are equal is if all coefficients match. So let's match up the coefficients. This tells us that 1 and c are equal, and b plus 2c is 0, and a plus b plus c is also 0. And look, we get a system of linear equations. We know how to solve this. C is equal to 1, b is equal to -2, and a is equal to 1. So x squared is a linear combination of the three polynomials. So we will write it as such. So here 1 is because a is equal to 1, and -2 is because b is equal to -2. And this 1 here is because c is equal to 1. We should do a sanity check that this linear combination of the three polynomials is in fact equal to x squared. And yes, that is true. Other linear algebra type questions we can ask would be, can we write a polynomial as a unique linear combination of a set of polynomials? We will visit this idea in a future lecture. Bear in mind that numbers like 0, 1, and 7 count as polynomials. They are called constant polynomials. Recall that the degree of a polynomial in X is the largest power of X with non-zero coefficient. For convenience, we set the degree of the zero polynomial as -infinity. Instead of working with the vector space of all polynomials, we can work with, say, the set of all polynomials with degree at most 3. This smaller set turns out to also be a vector space. This is the notation for the set of polynomials with degree at most n. P1 is a set of all polynomials of degree at most 1. So it consists of polynomials that looks like this, ax plus b, where a and b are real numbers. For P3, this consists of cubic polynomials, quadratic polynomials, linear polynomials, and constant polynomials. For example, this cubic polynomial is in P3, this quadratic polynomial is in P3, this constant polynomial is in P3, but polynomials like x to the 4th is not because 4 is bigger than 3, and this polynomial has degree 8, so it is not in P3. P0 is just the set of constant polynomials, so P0 is really the same as the set of real numbers. A common thing that people study is a sequence of real numbers. By a sequence, I mean an infinite list of real numbers. Here are some examples. This is the Fibonacci sequence. I can also have a sequence of odd positive numbers. This is a sequence of prime numbers. I can also have a sequence of all powers of 3 and a sequence of numbers. Unlike sets, the order in a sequence does matter. The set of sequences turns out to be a vector space denoted by boldface S. Addition and scalar multiplication are defined term-wise. So the world of sequences is a world in which addition and scalar multiplication make sense. So the set of sequences is a vector space. It's yet another world where we can do linear algebra. We can also consider the set of all matrices of the same size. I can add two m by n matrices and get another m by n matrix. I can multiply a matrix by a number and get a matrix of the same size. So this is another world where we can do addition and scalar multiplication. So it is a vector space. The set of matrices of any fixed size is a vector space. A function is called smooth if it is defined everywhere and all derivatives are defined everywhere. Most functions you're familiar with are smooth. For example, sine x, cosine x, e to the x, they are defined everywhere and they can be differentiated as many times as you like. Every polynomial is smooth. They are defined everywhere and their derivatives are other polynomials, which are defined everywhere. The set of smooth functions also include sums, multiples, and products of smooth functions. In particular, sums of smooth functions are smooth and scalar multiples of smooth functions are smooth. So the set of smooth functions of X is a vector space. It's denoted by C infinity. This is a huge set that contains most functions you can imagine. For this reason, it is hard to work with this set. But the fact that it is a vector space allows us to approach this very complicated set from the perspective of linear algebra. For example, this allows us to turn differential equations into a special case of linear algebra. We will talk a little bit about this in the next lecture. We will also talk about how to show that a set is a vector space without having to check each axiom directly.